Welcome everyone. Today we're going to be talking about oxidation reduction reactions, also known as redox reactions. One of the things you need to know is the difference between what is oxidation versus reduction. Oxidation is the loss of electrons, whereas reduction is the gain of electrons. In order for this to happen, there's going to be a transfer of electrons from one substance to another. In other words, oxidation and reduction must always occur together. Somebody has to give or lose electrons while the other one has to receive or gain electrons. One good way to remember who's who is by the acronym oil rig, where oxidation involves losing electrons, whereas reduction involves gaining electrons. This is a great way so that you don't confuse which is which. At the end of the day, when you have an oxidation-reduction reaction, there is going to be a transfer of electrons, which, by the way, is what drives synthesis reactions, decomposition, single replacement, as well as combustions. So here we have oil rig as one way to remember it. It's an acronym. Another popular acronym is Leo the Lion says grr, so you can pick whichever one you want, as long as you remember who's doing what. So to summarize, keep in mind that oxidation is the loss of electrons, reduction is the gain of electrons. But then we have something very interesting that could be confusing. This can be a play on words. The oxidizing agent is the substance that's being reduced. I'll go over this towards the end of the video so that you can understand the difference between an oxidation versus an oxidizing agent. And then you have reduction, which is the gain of electrons, versus what is called the reducing agent, which is the substance being oxidized. Notice there is a backwards here from one to the other, and we'll address that towards the end of the video so that you can understand how the word oxidizing agent and reducing agent are being used. So again, as a summary, the loss of electrons is oxidation. Gain of electrons is reduction. We know that one cannot occur without the other. They have to be coupled together. And these reactions, where there's a transfer of electrons, are called redox reactions for short. Now, what we're going to do is we're going to learn in this video how to assign oxidation numbers to each element, okay? And there's a set of rules that we're going to go over, and we're going to learn, some of these elements, like, for instance, fluorine has a specific oxidation number, whereas other elements have multiple oxidation numbers. So we're going to go through the different scenarios. Let's start with the first rule here on how to assign oxidation numbers. So if you have an element that is in its elemental form, it's neutral. The oxidation number will be always equal to 0. For instance, iron by itself, the oxidation number is 0. Okay, it's neutral. You could even put a 0 there, but it's neutral. Any element by itself. Okay, so zinc would be another. It's neutral. Okay, so a lot of times you'll see that we'll just put a 0 there. And that just means that the oxidation number is 0, and that is any element by itself. Now, here's the next one. The oxidation number of a monoatomic ion is the same as its charge. A monoatomic ion would be an element that has a charge, an ion basically. So let's take iron. If you see that iron is +3, the oxidation number, according to this rule, is the same as its charge. So this one has a +3 oxidation number. Okay, let's do another one here. Let's say you had calcium +2. So this one, the oxidation number is +2. Okay, or silver +1. Again, the oxidation number is +1. So a monoatomic ion, which is just an element that is charged, the oxidation number will be equal to that charge. Now, let's look at other scenarios. Nonmetals usually have negative oxidation numbers, but you will see some examples in a bit where it can be a positive number. we're going to focus on oxygen in this rule. Normally, 99% of the time, you'll see that oxygen will have an oxidation number of -2. So when you have any doubts, just put -2 and you'll probably be correct. However, there is a scenario where the oxidation number of oxygen is -1, and that would be when you have something called a peroxide. In a peroxide, there's a polyatomic ion that looks like this. It's O2 -2. Think about it. The entire charge is -2. But in this polyatomic, each oxygen has a -1 charge, not -2. Examples of peroxide would be something like hydrogen peroxide. That's a very popular one. The oxygen here has an oxidation number of -1, not -2. Here's another peroxide, sodium peroxide. Notice how the 2's don't cancel. Lithium peroxide. You see, you could tell because notice how the 2's do not cancel. Okay? So when you see a peroxide like this, the oxidation number would be -1. Later, I'm going to show you a scenario in which oxygen actually has a positive oxidation number. We'll do that a little bit later after I cover fluorine. Now let's go to hydrogen. Hydrogen usually is actually +1. Now hydrogen is +1 when it's combined with a nonmetal. And when hydrogen is +1, you'll usually see it written in front of the compound. Here, hydrogen is +1 and chlorine is -1. Okay? When you see hydrogen written at the front end, like this, it's safe to say that it's +1. Here's another example. Okay? Here's a few examples. So hydrogen at the front, when it's combined with either a nonmetal or a polyatomic ion that's negative, the hydrogen will have a +1 charge. However, there is a scenario where hydrogen has a -1 charge. Here you will see that hydrogen is actually written second because hydrogen is combined with another metal. Here's an example: lithium hydride, sodium hydride, potassium hydride. Notice that hydrogen is combined with a metal. Lithium, sodium, and potassium are metals. Notice how hydrogen is written at the back end. So here the metal is the one that's +1, the potassium for instance, and the hydrogen here would be a -1. Usually, most often than not, hydrogen will have a +1 charge, but I wanted to show you that scenario where it's -1. Now, this rule should be easy to remember. Fluorine, okay, which is a non-metal exclusively, will always be -1. This will never change. I wanted to show you a scenario where oxygen actually has a positive atomic number. And if you notice, and we're going to go over the rules in a minute, but in OF2, we will learn that oxygen actually has a positive number. Okay? And I'll show you how to figure that out in just a moment. That would be a scenario where oxygen is positive because fluorine will always be -1. Now, what about the other halogens? Fluorine is a halogen, but it's always -1. But the other halogens, which would be chlorine, bromine, and iodine, these guys, according to this rule, are usually -1. However, the only time that they are not -1, when they are combined with, for instance, oxygen, which they're known as oxyanions, or even fluorine. We're going to focus on oxyanions, which is more common. If you see chlorine, bromine, or iodine with oxygen, you will see that they are actually going to have a positive charge. Now, I will go over these examples in a moment. I'll use, perhaps later on, I'll use this example. This is the polyatomic ion chlorate, ClO4 -1. And notice that chlorine is combined with oxygen, and I will show you how chlorine actually has a positive. Okay? If oxygen is not present, or fluorine for that matter, the halogens, which are chlorine, bromine, and iodine in this example, they're always going to be -1. Okay? The one that is exclusively -1 will always be fluorine. Next rule, this one should be pretty easy. If you belong to group 1, you are an alkali metal. All alkali metals have a +1 charge. Okay, here's some examples. Sodium, potassium, rubidium, they will always be +1. Now the alkaline earth metals, which belong to group 2, they will always be +2, such as calcium will always be +2, magnesium, strontium, anyone from group 2, which is an alkaline earth metal, they will always have that +2 charge. Now, here's what we're going to do. We're going to put these rules together now so that we can assign oxidation numbers to each element, whether it's by itself or within a compound. And the two rules that we're going to go over is, first, the sum of the oxidation numbers in a neutral compound is 0. I'm going to address that rule in just a second. And then the second rule is that the sum of the oxidation numbers in a polyatomic ion would be equal to the charge of that ion. Now, I will go back and show you how to apply these rules in just a moment. Here I have a few examples, and what we're going to do is we're going to learn how to assign oxidation numbers to each of these species, and we'll go over which rule applies. Now, earlier I mentioned that elements have an oxidation number of 0. What I did not mention earlier, which I will include now, is that an element and a diatomic. So let's write both here. Elements and diatomics. Bromine is a diatomic molecule here. Their oxidation numbers will be 0. Okay? So whether you're an element or a diatomic, the oxidation number will be 0 for those. Letter B is something we did address, because in letter B, we said that the oxidation number would be equal to the charge. This is an example of a monoatomic ion. So since you see a +1 there, the oxidation number for this potassium ion is +1. Now, C and D, we're going to use the first rule right over here. It says that if you have a compound, that the sum of the oxidation numbers in a neutral compound is 0. LiF is a neutral compound, okay? So, this is how we do this. Now, I know we have a rule for lithium and fluorine, but let's say we had no idea what the oxidation number for lithium was, okay? Let's call lithium X, all right? Well, fluorine we know is always -1. Here's how you set this up. I'm going to show you the algebra. The sum of lithium and fluorine, which is -1, according to the rule, has to be equal to 0. When you solve for X, X algebraically would equal to +1. Now we can confirm that because we knew that lithium is +1, whereas fluorine is -1. We knew that from our rules. But now watch how in part D, I'm going to have to apply this rule because carbon we do not know, okay? Take a look at this. Carbon, which is a nonmetal, I'm going to show you how this nonmetal actually ends up having a positive oxidation number. So let's put CO2 here, carbon dioxide. Since we don't know, we don't have a rule for carbon, let's call it X. So according to the rule, the sum of the oxidation numbers in the neutral compound is equal to 0. Now we know that oxygen is -2, but look at this. There are 2 oxygens. So here's what we got to do. We got to multiply that by 2. Each oxygen is -2, but we got 2 of them. Now we're going to set that equal to 0. So X plus -4 after you multiply is equal to 0. When you solve for X, X is equal to +4. So in this example, carbon is +4 and each oxygen is -2. Okay, let me go ahead and fix that a little bit here. So there you have the 2 oxidation number. So when you have a neutral compound, you set it up equal to 0. Now, there's another rule that we're going to apply for letter E. Notice it's a polyatomic. So look at this second rule down here. If you have a polyatomic ion, instead of equaling the charge to 0, you're going to equal it to the charge of that ion. So we're going to look for sulfur. We don't have a rule for sulfur. Now, sulfur is a non-metal, but I'm going to show you how it ends up being positive because it's combined with oxygen. So here's what we're going to do. Let's call sulfur X. Okay? So X plus, now remember we got 4 oxygens, and each oxygen is -2. What we're going to do here, okay, let me go ahead and fix that. That doesn't look very good there. So what we're going to do here is we're going to equal it, instead of to 0, we're going to equal it to the charge. That's the only difference. When it's a compound that's neutral, you equal it to 0, and when it's a polyatomic, you equal it to the charge. So we know that X plus, this would be now -8, is equal to -2. If you continue doing the algebra, we're going to have here that X is equal to -2 plus 8, and we're going to get that X is equal to 6. So sulfur actually has a +6 charge up here, okay? And we know the oxygen is -2. Each oxygen has a -2 charge. So notice how sulfur has a +6 charge. Now we got one more here, and I don't know if you recognize it or not. It is a peroxide, but I'm going to prove to you how oxygen has a -1 instead of a -2 value. Look what I'm going to do. Let's put it here on the side here. So what we're going to do here is we know that we have 2 sodiums. Now, sodium's an alkali metal, so we're going to put +1. But there's 2 of them. And what we're going to do is we're going to call this X. We're going to look for oxygen, but there's 2 of them, so let's call it 2X. And I want you to equal that to 0. Okay? I know we're running out of room there, but let me fix that up a little bit. And we're going to equal that to 0. So let me put here plus 2x equals 0. And we're going to do the algebra. Well, we know 2 times plus 1 is just 2. Plus 2x is equal to 0. 2x is equal to -2. When you do the algebra, x is going to be -2 over 2, which is -1. So you'll notice that the sodium, okay, in this problem has a +1 charge. Each sodium is +1, and we just found algebraically that each oxygen is -1. And again, that's because it's a peroxide. Okay? Now, let's see if you guys can apply the rules here. Okay? For these examples, I want you to pause the video. Go ahead and try these, and then when we're done, we'll check that. So go ahead and pause the video. All right, hopefully you were able to do these. All right, so on the next page here, I have the answers to these, okay? And I think it's safe to say that the first 2 are pretty easy. Whether you're an element or a diatomic, remember that we said the oxidation number is 0. This one here is a monoatomic ion, and we said that the charge is, the oxidation number is equal to the charge, so this one's equal to +2, okay? And then here's what we're going to do with this next one. Let's call calcium, that guy is an alkaline earth metal, so let's put +2. So since this is neutral, this +2 is, if you put calcium plus chlorine, there's 2 chlorines. Let's solve for chlorine. It should be -1, but we're going to confirm it. We're going to put it's equal to 0. So when you do the algebra, 2 plus 2x is equal to 0. 2x is equal to -2. As I continue to do my algebra, you'll see that I'm confirming that it's going to be -1. Okay, so let's highlight the answers here. So calcium, we said, is +2, and chlorine there is -1. Let's do the same thing here for this one. So let's call carbon X. Okay, so let's put CF4, and then we'll call this X. Remember that there are 4 fluorines, and we said fluorine is always -1. So let's put here 4 times -1, and we're going to equal it to 0 because it's neutral. So when you do the algebra here, you got X plus -4 is equal to 0. So X is equal to +4. So carbon in this example is +4, and we have -1 for fluorine, which is in our rule. Okay, now we'll do the next two on the next page here. So notice this one's a polyatomic. Notice I got the answers here on this side here so we can check it. But let's go ahead and let's confirm the NO2 negative, which is called the nitrite polyatomic ion. So let's call nitrogen X. We know that oxygen is usually -1, and there's 2 of them. So let's put 2 times -2, but we're not going to equal it to 0. We're going to equal it to its charge because that's what the rule says. So when you do the algebra, we know that this becomes -4 over here, and that's equal to -1. So X is equal to -1 plus 4. X here would be 3. So notice that nitrogen, being a nonmetal, ends up having a positive number. Notice whenever you're with oxygen, if you're another nonmetal, whether it's sulfur, carbon, nitrogen, phosphorus, notice how it has a positive charge. That has to do, you'll learn this in the future, oxygen is a more electronegative element, and that's why oxygen is the negative and the other nonmetal is the positive. So this one's +3. And we know that oxygen is -2. And then look at SO3. We'll do this up here. So let's solve for sulfur. So X plus, we got 3 oxygens, each at -2, but we're going to equal it to 0 because it's neutral. So X plus -6 is equal to 0. X is going to be 6. So the sulfur here is a +6, and the oxygen, as usual, is -1. Okay, now I did want to show you a scenario where you have oxygen. The only member in the periodic table that's more electronegative than oxygen is fluorine. So I'm going to show you how oxygen is actually positive here. So let's put X for oxygen. We know that there are 2 fluorines. Each fluorine is -1. Fluorine will always be -1. When you do the math here, okay, you got -2 is equal to 0. Notice that oxygen in this scenario would be the only time where it's positive. Every other time, oxygen ends up being a negative number, whether it's -2 or -1 as a peroxide. So I hope these were good practice questions. Now, there is one final thing I want to go over. I'm showing you here a synthesis reaction. A synthesis is an oxidation-reduction reaction. Notice how sodium is neutral, so it has an oxidation number of 0. Chlorine is diatomic, which the same rule says it's 0. Okay, there's 0 because of the first rule. Now, in NaCl, Na is +1 and Cl is -1. You could either uncrisscross these, or you could do the algebra that I just did. I want you to notice that sodium went from being 0 on the left to +1 on the right. He is the one that lost 1 electron. So sodium is the one that underwent oxidation. Sodium got oxidized. He lost an electron. Chlorine went from 0 and it became -1 on the right. So chlorine gained an electron. So since chlorine is gaining, it underwent reduction. Now, here is the play on words. Sodium underwent oxidation. Therefore, sodium is known as the reducing agent. When you attach the word agent, notice how everything is backwards. the one that undergoes oxidation is the reducing agent. Chlorine gained electrons, so it underwent reduction. Therefore, chlorine is the oxidizing agent. This is a play on words. A lot of times students get confused by this. But when you add the word agent, it's the opposite. I'm going to show you one more example. Here we have a single replacement reaction. Elements by themselves have oxidation numbers of 0. So hydrogen being diatomic is also 0. Hydrogen here is in the front. It acts as a metal, so it's +1. Chlorine is -1. Here, remember, if you uncrisscross this, that's one way of figuring it out. Magnesium's +2 and chlorine is -1. Notice how magnesium went from being neutral on the left to being +2 on the right when it became MgCl2. He goes from being 0 to +2, so he lost 2 electrons. Therefore, magnesium is the one undergoing oxidation, and if he's undergoing oxidation, that makes him the reducing agent. Let me fix that up. He is the reducing agent. Okay? And now we're going to do the same thing here with the other one. Remember, in a redox reaction, you have to have both. Somebody undergoing oxidation, somebody undergoing reduction. So now we got hydrogen. On the left here, we got HCl. The H in HCl is +1. But on the right, the H becomes neutral. When you're going from positive and you're going to 0, or you're lowering, or you're going towards the negatives, it's because you are gaining electrons. So here, the hydrogen went from being +1 to 0. It gains 1 electron here. Okay? Since he's gaining electrons, he underwent reduction. And if you undergo reduction, that means that HCl is the species that is considered the oxidizing agent. Okay? So the one that is undergoing oxidation is the reducing agent, which would be magnesium, and the one undergoing reduction, which is the HCl, specifically the H within the HCl, he is gaining electrons, so he would be considered the oxidizing agent. Okay, so it's a little play on words, but I hope that I can point this discrepancy out so you don't get confused. Okay, so we will be seeing more practice problems on this, and in our one of our future lessons, we're going to learn how to balance these oxidation reduction reactions or redox reactions.